So let's talk a little bit first about molecular orbital analysis of cycloadditions, example of which being the Diels-Alder reactions we just learned about on last Tuesday. Well, I guess when you watch this might be far in the past Tuesday, but the Tuesday before spring break. So let's take a look at the simplest example of a Diels-Alder reaction cycloaddition. And that'll be one in which the 1,3-butadiene reacts with ethylene. And what we know is we know that these two molecular orbital diagrams right here, these are the molecular orbital diagrams for those compounds. So we got the highest occupied molecular orbital and the lowest unoccupied molecular orbital for each of them. And we even have with the signs or phases, as they're sometimes called, of the p orbitals that make up these molecular orbitals, what they are, indicated by the blue and the red coloring. And what we find is that in a Diels-Alder reaction, the HOMO of one compound must interact with the LUMO of the other. And that's because the electrons in that high occupied molecular orbital are going to fill or flow into the unoccupied lower and lowest energy molecular orbital in the other compound. So if that's the case, when we analyze this reaction with our molecular orbital diagrams, that is the pictures of the orbitals themselves, we're able to observe that if that's the case, and as these two molecules come together and line up physically in space, we'll see that the phases, as we call them, or signs, mathematical signs, positive or negative, of these, what are essentially mathematical functions, these p orbitals that make up these molecular orbitals, the sign of them match as they come together. There's a matching of the sign based on how the phases are in these different molecular orbitals of these two pieces that are coming together. And that's what's defined as the conservation of orbital symmetry, or what we oftentimes call in physical chemistry that these processes must be symmetry allowed. The symmetry of the phases must be matching as these two compounds come together reacting. Ultimately, once they come together, the hybridization does change from being sp2 around the carbon, where these are p orbitals, to becoming sp3, and the orbitals that were once p orbitals now become sp3 hybrid orbitals that are overlapping. But regardless of that, it's still based on the phases of the p orbitals that we're able to make these determinations. So let's take another reaction that's a cycloaddition, much like the Diels-Alder, but we don't call it that, where the Diels-Alder is a 4+2 cycloaddition, which means 4 electrons on one of the reactants is moving around and 2 pi electrons on the other reactant is moving around. Here we have 2 pi electrons on one of the ethylenes and 2 pi electrons on the other ethylene. That's what's going to cycle around in this pericyclic reaction. And as such, we call it a 2-2 or a 2+2 cycloaddition. Now, what we observe is if we were to, think about this like we learned for cycloadditions, this electron comes up like this. These electrons come down like this, and you form these sigma bonds as that happens, and you form this cyclobutane. Now, what's observed is this reaction does not happen no matter how hot or cold you have it at. So heating it thermally doesn't make the reaction happen. And the reason for that, if we take a look at the molecular orbitals and look at the HOMO and LUMO of these molecules, we observe that if you were to put them in space and orient them in space and bring them together, it is not symmetry allowed, because the reaction happening is determined by that symmetry allowed requirement. So what we're doing is we're saying the electrons in the HOMO of one ethylene is flowing into the empty orbital of the LUMO of another, and those are the phases of those p orbitals that make up those molecular orbitals. So keeping that in mind, that for the HOMO, the phases are in sync with each other, whereas the LUMO, they are out of sync. When you then bring those two pictures together, you observe then that for at least one of the pair of p orbitals that would be overlapping, the phases can't match. And it doesn't matter because you do have the ability to kind of rotate around the molecules and try the two different orientations, but it doesn't matter. No way can you make these two p orbitals both line up in phase with the two p orbitals of the other molecular orbital. And because that it's symmetry forbidden, the reaction does not happen under these thermal conditions where these are the molecular orbitals of the molecules that are the highest occupied and lowest unoccupied. What we do observe is when you put them under photochemical conditions, or in other words, just when light is shining, it'll be noted in the reaction arrow, as you see there, with the H nu in the reaction arrow. If it's a thermal, you'll just see it either a triangle, which represents heat oftentimes, or it'll say heat, or it'll give a high temperature of like 100 degrees or 200 degrees Celsius. That would mean thermal conditions, where if it's light, you'll usually pretty much either see the word light or H nu. When light is exposed to ethylene, of the correct frequency at least, you're able to excite the electrons in the highest occupied molecular orbital into the lowest unoccupied molecular orbital, like we learned about in a previous play posit. Having done that, you've now changed the phases, at least for some of the molecules. Not all of the ethylenes will always be excited by the light, but those that are in an excited state, they now have a different molecular orbital diagram with different phases for their HOMO versus the old one. And if you now think about it, if you take the excited ethylene and take its electrons in its highest occupied molecular orbital and move them into the lowest unoccupied molecular orbital of an unexcited or ground state ethylene, you will note then, if you look at those two molecular orbitals now, that they are phase symmetry allowed. They are in sync with each other, the phases. So that's what we're going to do also when we talk about the electrocyclic reactions in lecture. That will also have a molecular orbital analysis where we're trying to make sure that we are doing the reaction. In that case, for the electrocyclic, there'll be some rotations of carbon atoms, which will determine where the groups are pointed in space, and it'll kind of essentially determine the stereochemistry outcome of the products. That's going to be determined by the phase symmetry allowed nature of these reactions, that the phases of the p orbitals have to overlap and match. So let's talk a little bit now about sigmatropic reactions. So sigmatropic reactions are the third category, electrocyclic being the second that we're going to talk about in lecture. The third category of pericyclic reactions. In this one, the net transformation is really just the position of the sigma bond. You're not really forming any more or less bonds. There's not a net change of anything, but you're moving the position of the sigma bond and replacing it with a new sigma bond in a different spot. And the location of the pi bonds move as well, but there's not a net gain or loss of any like some of the other pericyclic reactions. One thing to note about sigmatropic is they have this kind of weird notation. It's not really, locants like we normally think about them used in nomenclature, but it's still a numbering of the carbons, kind of like there's a special numbering for the conjugated diene electrophilic additions, where it's like 1, 2, 1, 4 addition. We got some new ways of numbering. And essentially, when you have a sigma bond changing or breaking and forming, you number the carbons from the spot where it's being formed to the spot that's being broken. Now, sometimes it'll be one continuous numbering of atoms. If it's happening right next to each other, the sigma is just moving one over. But if it's in the middle, if it's moving from one side to another of this piece, as we'll see in a moment, you have to number it, the two pieces separately. So in the case of this one, because it splits it right down the middle here, the formation and the breaking and the formation of the sigma bond, we number the two pieces in that transition state. So you're essentially looking at the transition state when you do this numbering. So all of the bonds that are forming and breaking are all dashed lines, and that creates these kind of, being that there's no solid line between the two sides of the molecule, we have to number them separately. So this gets numbered 1, 2, 3, this gets numbered 1, 2, 3, and then the name of this sigmatropic reaction is a 3,3 sigmatropic, because the new sigma bond is forming at the number 3 carbon and the number 3 carbon of the other piece. or of the two pieces. And here's one, the 1,5 sigmatropic addition is one where you still have two pieces, but the second piece is just the hydrogen atom by itself, so it just gets numbered 1. And then the first piece is this chain of carbons on the other side of the two sigma bonds that are forming and breaking, and that piece gets numbered 1, 2, 3, 4, 5. And so the formation, which was over on this bond, is forming between the 1 and 5 atoms, and so it's a 1,5 sigmatropic rearrangement. What we're going to really narrow down into is 2 3-3 sigmatropic reactions that are very common. The first one is called the Cope rearrangement. Oftentimes they're called rearrangements because this repositioning and moving of the sigma bond. And so this Cope rearrangement is one in which, due to the fact that this chain of molecules can position itself where it kind of looks like it would be a ring, it positions itself in a way that there's able to create this flow of electrons. These pi electrons move here, these pi electrons move here, and these sigma electrons break off the bond, break away from the bond between these two carbons and form a pi bond right there. So that's the Cope rearrangement. And so now the pi bonds are now between these two carbon atoms and these two carbon atoms, and there's no new sigma bond between here. And so you take essentially a diene that's not conjugated, but rather isolated. But because it can arrange itself in this 6-carbon arrangement, and you can see that there's this flow of electrons, it's able to make this, explore this possibility. And when it does this sigmatropic rearrangement, whichever of the two structures has the more substituted alkenes, that's going to be one, and thus the more stable energetically, that's going to be the one that's the more favored product. Or I should say even the most favored structure, as it kind of equilibrates between the two structures. The other type of sigmatropic is known as the Claisen rearrangement. It's still a 3-3. The thing that separates it from the Cope rearrangement is one of the atoms is an oxygen atom. And it's the one that has to position itself in a way that it's found to be, its sigma bond is the one that's breaking the oxygen with the carbon that's allylic. So specifically, it's an allylic vinylic ether. So it's an ether because it's connected to two R groups. One of the R groups, it's connected directly to an sp2 carbon in a double bond. So that's the vinylic group. Vinyl is a term that's used for groups that are connected directly to sp2 carbons that are part of a double bond. Allylic is that name we use for when something is connected, or the position of the carbon that's connected to a double bond. So this carbon being connected to a double bond, anything that's on it will oftentimes be called allylic because this position itself is the allylic position, much like the benzoic position we talked about in chapter 17. And so it's the sigma bond between the oxygen and the allylic carbon is the one that breaks. But it does have to make sure that it has the pi electrons in these specific spots, because that's the only way you can get this cycle of electron rearrangement. And when you do that cycle of rearrangement and move that bond from the 1,1 atoms to the 3,3 atoms using that same number we showed earlier, we create what was once an ether to become now a carbonyl C double bond O, in this case an aldehyde, since there's an H coming off of this. And we form a new sigma bond. Once again, there's an equilibrium between this. There's an exploration, which is the one that's going to be the structure that's, by the end of that equilibrium, is the more favored structure. It's the one that has the carbonyl compound, which is a more stable or more energetically favorable bond than the carbon-carbon double bond. And so turning one of those two carbon-carbon double bonds into a carbon-oxygen double bond is a more favorable thing. So there'll be larger amount. It's not limited to vinylic ethers or allylic vinylic ethers, but also allylic aryl ethers, which is just the terminology we use for when a group is connected directly to a benzene ring. Oftentimes we call it also a phenyl ring. And so when the oxygen that's part of this ether is connected to an allylic carbon and to a benzene ring, this same Claisen rearrangement, 3,3 sigmatropic rearrangement, can occur. Now, in this case, once you see and find those two pi bonds that are able to do the cycling with the breaking of the sigma bond and forming the new C double bond O and the new carbon-carbon double bond, what we realize, and something that's very true for benzene rings, when there is a benzene ring that has, or what isn't a benzene ring, but a conjugated diene within a cyclohexane ring, and one of the other carbons that are conjugated with that diene, these two pi bonds, when it has a C double bond O, there's the possibility of tautomerization that we talked about. In other words, reverse from what we learned back in chapter 9 in OChem 1, you can take this C double bond O and transform it back into an enol, or what we called an enol back then, an OH that's connected to an alkene. Now, in this case, it's actually a phenol. It's an OH connected to a benzene ring. Now, unlike the enols that are less stable than the C double bond O, in which case the C double bond O structure is more favorable, it's actually the alcohol that's the more favorable structure in this tautomerization, even though it's connected to an sp2 carbon. The reason being, this benzene ring has the aromaticity we've been learning about, and that aromaticity is highly energetically stabilizing or favorable. So even though enols, where it's just connected to a regular double bond, are less stable than the C double bond O structure that it can turn into via tautomerization, it's the phenol structure that is more stable due to the aromaticity. And so you might be asking, what is with these things? They're mostly memorization, because, or just being familiar with that this kind of 6 atoms linearly in a row that can be rearranged in a way that we see that these 3 pairs of electrons can flow around in a cyclic manner and form this new structure. What's the purpose of that? Well, it's something to be aware of in synthesis, because if you can make this thing that can undergo a Claisen rearrangement, eventually get locked into this phenol structure, that's a way to make a phenol from an allylic aryl ether, which you could probably make that via maybe phenol, or there's ways you can make this structure from some of the reactions we've learned already, as well as probably future reactions that we're going to learn about. So if you know that when you make something like this, it does transform via Claisen rearrangement and tautomerization into this structure, you know that that's what you ultimately can actually make, is this, by creating a allylic aryl ether. Another reason to mention this and be familiar with sigmatropic is sigmatropic rearrangements occur a lot in biosynthetic pathways of important molecules in the body, such as vitamin D. So vitamin D starts with this kind of steroid-like shape, but then due to the transformations that get it to this stage, once it's in this molecule, it's able to undergo first an electrocyclic reaction that we're going to learn about in lecture and open up. And then once it opens up, it's able to undergo a type of sigmatropic rearrangement. And that sigmatropic rearrangement just moves those sigma and pi bonds around. And that's what's in that pathway that you'll learn probably more about in biochemistry. Well, that's it for this play posit. I'll see you in lecture on Tuesday. Bye.